Hello everyone, my name is Greg Risterman. I'd like to welcome everyone today to this Olympus webinar titled Introduction to Guided Wave Inspection Theory and Technology. In addition to the guided wave introduction, attendees will learn about the powerful benefits of this solution and its advantages and limitations for pipe inspection as a screening tool and part of an overall NDT program. Our presenter today is Nick Bublitz. Nick is a global product support specialist with Olympus and has been working with portable and automated systems for 8 years. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen. If we don't get to your questions, we will address them either by email or phone after the event is over. Now, without further ado, I'd like to turn this presentation over to Nick Bublitz. Nick, take it away.
Thanks, Greg. I want to second Greg's welcome to you all. I know at certain parts of the world it might be quite early in the morning, so thank you first and foremost for joining us today. As Greg said, the goal of this webinar is to give you a basic introduction to guided wave, try to go through the technology as well as some of the equipment. So we're scheduled for about an hour. We'll have time, hopefully, for a little bit of question and answer at the end. I'll try to answer all your questions, and if we don't get to them, we have ways to answer them after the presentation. So without further ado, we'll go ahead and get started. So basically, as we all know, if we're involved with the NDT business, today's inspection challenges are becoming more and more focused on high productivity along with high quality results. As many of you know, if you have Olympus products or you're familiar with the company, we have a very strong pipeline product offering. And about a year ago, we decided to offer a commercial guided wave system. It's Olympus's first foray into guided wave technology. Basically, it's a solution for corrosion and metal loss detection, basically focused on pipes. So what we're trying to do in these next slides this morning is both the basis of guided wave theory, so you have a basic understanding of how the technology works from a theoretical perspective, as well as what the actual equipment does, and go over the system itself, a typical inspection, and how it fits into the efficiency of a corrosion management program. So look, just very basic, if we want to do a very high-level review of what guided wave ultrasonics for pipeline inspection is used for, it's basically a system that's used to screen in-service pipes and pipelines over long distances. And we'll go over a little bit more specifics as we go along. One of the big, huge benefits of guided wave inspection is we can actually inspect pipes with limited access. And there's a laundry list of different access restrictions that can be present in a pipeline, and we'll look at that. And basically, the overall result is we can very accurately pinpoint locations that require further inspection, which ends up saving a lot of time. And we'll look at the details of that. Overall, if we implement a guided wave system along with other complementary NDT, we can provide significant reduction in operating cost. If you look at guided wave ultrasonics, if you Google it or look it up, read scholarly papers, you'll also see it referred to as LRUT, or long-range ultrasonic testing. So here's our basic agenda today, and we have this fed throughout the presentation so we kind of see where we're at. We're going to look at the basic applications in industry that guided wave for pipe is usually used. Go over a very simplistic basic of the guided wave theory. Go over a basic guided wave system, of course focusing on the Olympus system, but most systems have the same basic qualities. We'll look at what an inspector that was using a guided wave system would typically do for a typical inspection sequence all the way from the setup to the pre-planning, reviewing data, and doing their reporting. We'll take a quick overview of what standards codes govern guided wave today. Which ones are in works, try to take a global perspective on that as much as possible, and also look at the typical training paths. If somebody was to buy a guided wave system, what it would take to conform to the standards and codes and also be efficient in operating it. And then we'll have a conclusion kind of reviewing some of the major points. So we look at some of the basic industries. This list is by no means all-inclusive. Anywhere there's pipelines, there's a potential. or pipes in general, there's a potential to use guided waves, but these are some of the places we see guided wave systems used the most. Refineries, power generation plants, pipes and piping and gas transportation stations, onshore pipelines, offshore risers and other piping systems that are offshore, and then transportation with DOT piping. So look at some of the general applications we see the guided wave system used in. One of the main obviously being corrosion detection in both in-service pipes and pipelines. That can be very basic above ground conventional pipe, and also might be coated pipe, and we'll talk about those details in the slides coming up. Detection of corrosion at supports and pipe racks. As you can see in the illustration, it's using not a freestanding pipe. We need to support that in some way. So we'll go over the details of how guided wave could be used in those instances. Inspection of through-wall pipe. So if we have some type of manufacturing facility, a refinery, some type of business that has pipe that actually is somewhat encased in a wall, we can look at how guided wave can help us perform NDT even in the sections that might be encased. Corrosion detection in service pipes and pipelines, just a few more examples. Corrosion under insulation, very popular topic today in the NDT community. Everybody wants to know the best way to test for these type of things. Obviously, removal of insulation can be a tedious process, so we'll talk about how guided wave can help with pinpointing the areas of concern. Inspection of buried pipe, so without having to dig up a full trench for the total area of the pipe. We'll talk about how a guided wave system can fit into those applications. Vertical pipes, pretty much the same thing. We want to inspect from, say, the bottom of a vertical pipe. Guided wave can be a very efficient way without putting scaffolding up to the total area to inspect it 100%. How guided wave can pinpoint the areas that we should look at first. And, of course, road crossings. So the applications, so basically with guided wave, generally what we're trying to do is avoid unnecessary excavation, removal of all the coating, putting up complex scaffolding to inspect 100%. And guided wave can help avoid the unnecessary levels of these things if no flaws are detected. But in its base, it really is a screening tool. We'll see further in the presentation what data is output from a guided wave inspection. And then the need to address those areas with other NDT. Of course, with Olympus products, so if they're take an ultrasonic perspective, anything from a corrosion gauge, thickness gauge, flaw detector, or a more advanced phased array corrosion mapping approach. But typically what we do is pinpoint those areas, and if we want hard concrete values of wall loss, we'd go back with some other complementary NDT. Could also be, OD laser screening or something like this. That's just a very brief overview of the applications industry, so we'll go ahead and continue on to the basis of guided waves. So if you think about what we know about conventional ultrasonics, typically what we're dealing with a flaw detector, a thickness gauge, phased array system even, we're doing a very localized inspection. I mean, in the area that we need to inspect, if it was a pipe, we'd have to prepare the pipe over every area we wanted to inspect, put a sensor on it, either move it manually or some type of automated, semi-automated system that would help with the movement of the probe. But all of our inspection is really in a localized inspection area, either directly under the sensor or in the case of angle beam, maybe near the sensor. To do this with ultrasonics, because we normally need a couplant, we need access to that localized area, we must remove completely 100% of the coverings. We must condition that pipe where the sensor is going to be placed for surface roughness. It can be a very tedious type inspection. And what we're typically looking at there is using a corrosion gauge and doing very small point measurements or some type of mapping system like hydroform corrosion mapping or a conventional UT corrosion mapping system where we're mapping the whole area. One of the big differences with guided waves or long-range ultrasonic testing is the ability to screen an entire pipe region. So we will basically have a long inspection range in comparison. So if we put a collar at a certain location on a pipe, we can actually do a very long inspection range of about 182 meters to 600 feet in optimal conditions. And we'll discuss those conditions a little further as we go on. And this is actually in both directions. So you can see in the illustration there we have probes placed, and we're able to actually go down a significant length of the pipe and get ultrasonic results back without having to necessarily treat, condition, remove coatings of all those areas. So we look at the basis of guided waves. We typically operate in a frequency range of about 15 kilohertz to 85 kilohertz, so a lot different than what we might be used to with our traditional flaw detectors or even phased array ultrasonics. Guided wave's been around for quite a while, starting around the 1920s. In the NDT community, it's really been heavily used in about the 1990s, which seems like it's been a long time now, but as we know with new technology and NDT, it takes a significant amount of time before certain techniques are recognized and standardized and people really buy into them. So if you go do research on guided wave systems, you'll see there's many different types. One of the key things we want to focus on here is our system is a piezoelectric sensor or probe system. You'll see some other EMAT type guided wave systems out in the industry used in both research and now being applied in general NDT. So these are the same type of general manufacturing practice that you would think of with your conventional flaw detectors as far as the type of the sensor. We might be utilizing them slightly different in different wave modes, but they're basically the same manufacturing quality. And if you do that subsequent research, you'll want to hit on to make sure you're looking at the same apples to apples when talking about guided waves. One of the main confusing things for people is, with an NDT background and an ultrasonic background, is people are very used to longitudinal waves, shear waves, common practice in our NDT training. Guided wave typically uses different waves that we might not be familiar with. The main wave we use in a first scan acquisition is what's called a torsional wave. And we basically pulse this all around the pipe circumference to get 100% coverage down the length of the inspection zone. Now, without going into a very scientific, descriptive explanation of what a torsional wave is, if you can imagine having a coiled spring and pulling that spring on the ends and then releasing it, this is the type of propagation, a simple explanation of how that energy would actually be oscillating throughout the pipe medium. Our typical first scan, we call it an axisymmetric. So basically, it's a full 360 around. We're basically sending sound wrapping around the pipe and throughout the pipe body. And this is how we get the ability to do long-distance screening with this type of wave. One unique thing about it, conventional ultrasonics is very directional. We know if we take a shear wave sensor, we put it on a shoe, we're looking in the forward direction. Without complex, maybe dual matrix phased array probes, we don't really look in many different directions typically with ultrasonics. Guided wave systems typically, whether you look at the data or not, are pulsing from both sides of the collar, meaning if we look at our schematic or our picture on the bottom here, the operator has placed a collar. When he actually shoots that guided wave shot, we're actually going to have energy going in both directions. So it's a kind of a unique thing with guided waves. They can be useful in an inspection sequence, or sometimes people will cut down their display or plan their shots that they look only in the forward direction. But it's going to happen in a typical guided wave system. As far as inspection distance, again, from the probe collar 0, it's about 91 meters, 300 feet under optimum conditions, so that's going to shoot both ways again, for a total of about 182 meters or 600 feet for a total inspection zone. So you can see how this can be much more advantageous than having to put a sensor 100% down 600 feet of pipe. We're able to screen that pipe and decide where we go for complementary NDT. One key point is these are, potential distances. This really varies. The pipe, condition, what coating might be on it, the type of coating, how thick it is, the configuration of the pipe, whether it's a straight line pipe, whether there's bends, elbows, this type of thing. So we can really only give one specification. It's hard to estimate under certain conditions without doing a little bit more quantification of how far that distance would be under any given condition. So we're going to look at a little bit more of the basics and just see how guided wave typically outputs the results to us. We don't get an accurate measurement of wall thickness like we would with a thickness gauge. Thickness gauge, we couple it on, we go to a very defined area, and it spits out 2-3 decimal points of measurement, and we're able to quantify the wall loss very accurately. The nature of a guided wave is basically just detect a general change in the total pipe cross-sectional area. So for example, we can see 2 pipes of X diameter here, X thickness, and basically each one has a amount of wall loss shown here that would equal 5% cross-sectional area. To a guided wave system, these 2 different types of wall loss would generally look about the same. Obviously the specifics are going to play into that, but we're not going to get a measurement like 0.01 thousandths loss at 20 feet down the pipe. We're going to get a general classification or estimation of the amount of wall loss, and we'll look at how that works into everything as we go on. One unique thing, it is equally sensitive to OD and ID corrosion. System won't generally tell you whether it's on the OD or ID, and that's why we would have to go to that area. If it was a covered pipe, we'd then excavate at that point, visually look for OD corrosion, apply other complementary NDT techniques to figure out whether it's OD, ID, and get a quantitative measurement. But we can estimate the circumferential extent. So once we know the location, we also have several tools in the software that will tell us the clock position, if you will, of where that corrosion is generally located. So if we had a large area with covering, we would know that we want to remove 12 inches of coating or insulation right at that area. We do it at 3 o'clock versus doing the whole pipe, if that's where the tools have pinpointed the corrosion area exists. And again, as we've said all along, we generally, if we want that 3 decimal, 2 decimal measurement to get a final decision on how severe that corroded area is, we would use other NDT methods to validate the indications we find on a guided wave system. So what are the advantages? If it doesn't give us this value, why would we want to use a guided wave system? Typically, we're looking for high productivity inspection. As we mentioned, the long range coverage and very rapid screening. So if, again, we had that 600 feet of pipe, we wanted to pinpoint the areas that might have potential corrosion without taking all the insulation off, without completely excavating it from the ground, without building 100% scaffolding to be able to access the top of it. If we wanted to screen through the wall and say, well, this part of pipe that is stuck in the building might have corrosion here, we'd be able to do that without investing in all that upfront removal, scaffolding, etc. So it does give us that 100% screening, 360 degrees around the pipe circumference. And again, ability to scan those pipes with limited access, such as coated, insulated, buried, road crossings, and through wall pipes to get a general idea of where the corrosion exists. Which usually ends up, when we put this into a maintenance program or general use, is a very good cost reduction for all those things, not having to do them 100% all the time. So it really becomes a cost-effective solution for pipe integrity management programs. And in the case of in-service inspection, we can get a good screening of the pipe, know where to focus our NDT inspection without disrupting production. So it's a very general basics of the guided wave system, the theory and how it works. Again, we didn't go into too scientific principles on several things, but some of them will be supported as we go further into the presentation. So we'll go over just a general system overview at this time. Again, these will apply to most guided wave inspection systems. In general, we'll of course use our Olympus UltraWave system as the basis, so there'll be some specifics, but try to be pretty general as we talk about it. So here's a real small snapshot of what the basic parts of a typical piezoelectric guided wave system consist of. In this case, we have an ultrawave LRT or long-range box that actually does the inspection. We can see in the middle there. Basically, we can portable. It's fairly small size. You can see it in comparison to the handheld laptop there. So it's a very portable thing. We can actually put in a backpack, so it's easy to get around the job site. That's usually coupled with an acquisition computer. In this case, we have a touchscreen convertible tablet ruggedized for the field, which will actually host our software. There's no actual screen on the ultrawave. It's all done from this acquisition and analysis software on a laptop. Then we have a collar, including the probes. So in this case, we can just get a snapshot of the probes. If you see my red dot here, we basically have the probes aligned here. All our cabling coming out back to the guided wave system. And then we have basically a bladder system that is put over top of the probes. This will actually be coupled to the pipe using air, either a air pump, electric or battery operated, or even a simple foot pump, depending on the collar. Be to a certain PSI to ensure constant pressure, good results from the sensors. And we'll look at that in a little more detail as we go, but this is the basic parts of a guided wave system. So we have an acquisition unit, a computer of some type that's holding the setup, acquisition, analysis, and reporting software. And then we have our probe set, the bladders and the collars in order to accommodate different pipe diameters. A little bit further into some of the individual pieces. So we look a little deeper at the inspection collar. Again, we see it on a different pipe here and also laid out flat. So this, in this case, is a very flexible collar. We usually sell a guided wave system in predefined kits. So our standard kit would be a 2-inch to 24-inch OD pipe inspection system, which would provide all of the different bands, sufficient amount of probes, wiring, everything needed to go up to a 24-inch. Outside of that scope, we're able to produce bands that are larger. That possibility comes up. We also have kits that are a smaller range for people that might only do smaller diameter pipes. But we're going to be able to have all the transducers and all the tools necessary to do a certain range typically. Each individual collar will also have a bladder. It's not shown real well here, but we actually have a slightly more rigid band underneath that actually holds the probes, and then basically that would be put on the pipe, secured by simple Velcro usually, and then we put the bladder over top. We inflate to a certain PSI, and this is what pushes the probes down to make sure there's good contact between the pipe surface and the probe. Unlike most ultrasonics many of us might be familiar with, because we're operating at the 15 to 85 kilohertz frequency in the way the rest of the system works, we do not require coupling. So there's no need to spray water, use gel coupling, or some of the things we might be used to with traditional ultrasonics. One of the key features of the ultrawave system is this band is actually a very low profile design. We can see the thing there. There's not a huge rise. The actual probes are very short in stature, only about 1 inch from the bottom to the top. You actually see the 2 ultrasonic sensors built into the probe here. A very small contact surface, so when we inflate that bladder, we're ensuring very good contact. And if we had limited restriction because of another pipe over top, some other access region, it's very easy to get this band. It's very flexible into as many areas as possible in order to facilitate inspection in that area. Everything is really designed in order to be fast and easy to set up on the pipe. Again, position the collar with some considerations, inflate the bladder, and we're basically ready to go on a pipe. We will have to do, in good practice, maybe some conditioning. We don't want the pipe to be very rough, scaly, etc. The area that the probes are actually going to be touching, which is pretty small, we'd want to do a minimum amount of conditioning that we'd be used to in traditional ultrasonic inspections, just to make sure we're making good contact where we're putting the sound into the pipe. And then the idea behind our system is we really try to make it light and compact. Again, backpack for the units, and these bands are very flexible, able to be folded up, put into a thing. So if we have multiple bands we need to go out and do a job, they're relatively lightweight, able to be folded, put into Pelican cases, etc. So a little bit deeper detail on the laptop and a typical acquisition unit. So we can see here, this is a battery-operated unit, so we can bring it to places where portability is a necessity. You can open this bay door. There's slots for two batteries. We have probe connections that go to the collar itself, the individual sensors, which are coupled into a single wire coming back into the acquisition unit. Simple power button, some indicator lights, and a connection to the computer. So the general necessities of an acquisition unit itself are not that cumbersome or that complicated, because most of this work is done by the software unit. Just our pulser receiver type hardware is housed inside the actual acquisition unit. Again, that's a 16-channel, very broadband frequency range from 15 to 85 kilohertz. Typically the laptop, we can run it on multiple laptops. With our system, like any system, we do recommend the recommended one based on specifications and also durability for field. In that case, we use a GTAC V200 rugged industrial laptop where we can close all the ports in case we're in a dirty area. Very sunlight readable display, integrated camera for reporting purposes, these kind of things. So the basic features are all in the computer that we would try to sell with the system to ensure you have everything in the field and compatibility with the software requirements. So a little bit deeper look at the software. Guided wave systems made by other manufacturers will vary a little bit. Some of them will have a lot of similarizations as far as how the actual acquisition analysis is performed, but we'll use the UltraWave software as a guide here. Like many Olympus products, we try to make the setup easy. So one of the key features we think we have is a setup guide, or as we often refer to them in our products, a wizard. So basically, from the time you open to perform your first acquisition, it's kind of guided through the different steps instead of having to go through many menus. So we can see a little snapshot of that, and we'll have a better look at that in the next slide. But basically, we're in the setup pane right now, where we're just starting to set up for an inspection, and we actually have what we call a tree going on the left. Now, this is just like any Windows program, where if you open multiple files, you see the other files inside that folder. We're able to basically link down, close down, open these up, shut them down. If you can navigate a Windows type tree, we have basically everything we've performed or access to different parts of the software through that tree as we build and get more complex into the software. So we basically go in there, and we'll talk about more on the setup wizard as we go. One of the key features we have too is actually how we display our data, and this is very key and be able to sort through a large amount of data. We looked at the other slides. We obviously are pulsing many different probes at the same time, many different frequencies. Looking at one A scan at a time wouldn't be very efficient, so the software has to be able to lay out that information in a time-efficient manner in order to be able to analyze it efficiently. We'll talk more about focusing modes. So we have two different focusing modes with our guided wave system, one called active and one called synthetic. And we'll go into those in a little more detail when we get to those slides. And then obviously system software can be very good, but in the end what you have to provide your client or your own personnel in-house is some type of report. So we'll look at that as well, how the UltraWave software tries to make that as easy as possible and able to be used with other programs we might use for our reporting. So now we'll look at that inspection sequence and stop and look at some of those things that we looked at the system overview in more detail as far as how they fit into that inspection sequence. So this is a really defined list of what typically somebody would go through when they went out to do a guided wave inspection. So we see an operator here. He basically has the whole system with him. So the unit's actually backpacked here in a portable type position on a backpack. He's going out to his first shot. He's actually got the bands and collars pre-assembled for whatever diameter he's going to do. And here he's got his laptop and any complementary tools, including the air pump and everything else that he might have to do. So typically before we do any inspection, we'd want as much information about a pipe as possible. This could be done, quite a bit before the inspection if information between the service provider and the client, they have details about the pipe as far as how it was built, et cetera, or they do a visual walk. But what we normally do is a pipe sketch, which we'll see in the next one, because when we get to the analysis point, what we'll want to know is where certain features are, things like welds, visual supports, if we can see any corrosion. If we walk parts of the pipe, depending if it's visible or not, it'll probably note any areas of corrosion that he sees right off the bat and where their location is. So we typically have a long tape. We'll mark off, there's a weld every 20 feet. These will be used for different parts of the inspection and be able to help in the analysis feature. So we'll look at that in a little more detail, but the more information we know about the pipe, it makes the analysis that much easier and the inspection that much better. We'll look at collar installation prior to the shot. Again, a little terminology, but we'll look at that, what we call an axisymmetric scan, or that first scan that we usually do to start the inspection. Then we're basically going to go into individual color map and A-scan analysis, look for any areas that look of interest, potential defects, maybe do some different type of focusing, active as well as synthetic. And we'll talk about the difference of those. You can see the synthetic is something that's done during post-processing. So they might do this in the field. It might be something, once it gets back to a second level analyzer, they decide to do more, where active focusing needs to be done while the probe collar is on the pipe. So we'll look at those in a little more detail. And then at some point, defect confirmation, once we make some calls on what we see. Again, using complementary NDT, could be as simple as conventional UT or phased array. Maybe if the results warranted, they might do a second acquisition if necessary, and then final analysis and reporting. So this is a very quick laundry list, but we'll go into a little more detail as we go here. So this is just a really rough schematic of what a pipe sketch might look like. Depending on the pipe, the conditions, what we're dealing with. Obviously, this is going to change a little bit. But normally what we do is we'd walk and we'd measure and we'd lay out all of the features that we know about the area that we're going to be inspecting in that shot. Typically for a large project, we're going to be doing a lot of different areas of pipe. They would have a plan where these pipes should be positioned and what features are in the pipe might play into that. We want to be, certain distances away from a bend or a weld where we position our zero for each shot. So all this is typically laid out as much as possible. Things like bends in the welds, connections, welds. If they saw some visual corrosion, changing coatings. All this would be pre-planned as much as possible so that they can plan where to put the collar for each shot. And then as far as when they get data back, they're going to use this information to help with the analysis as well. So it can be as simple as a drawing on a piece of paper, or it could be something more complicated done in software, but a rough sketch to line up with the data. And then basically once we know where our 0 points or our inspection points are going to be, we go to that area. And we typically do some type of surface conditioning. It doesn't have to be abrupt depending on where we're trying to place the collar, but we, just like conventional UT, we take a wire brush, if there's some scale or the loose rust. We just try to condition that pipe as well as possible or well as we want to in the area where the pipe is actually going to be. So it doesn't have to be a large area, a couple inches, and in order for the probes to make good contact. The more attention paid to this, obviously it's a very good practice for any ultrasonics. Typically also before we place the band, we'd want to verify if we think the pipe is a certain thickness. We'd normally take 1 or 2, maybe 4 points around the area where the collar is going to be and just record that pipe thickness measurement, make sure it is what we think it is. Then typically we're ready to place the collar itself. So we mark that out where the 0 point is. Actually, the software allows you to make the zero of the band several different things, so it's somewhat flexible. We're going to position the lower band with the probes on it. Make sure it's fairly secure. You can see where it overlaps here, where we've made the connection on the flexible inner probe holder. We position a band, an inflatable band around it, or what we call a bladder. We have a port not shown in this picture, but using a battery-operated air gun or even a foot pump that we would use for like a bike tire. We're just going to inflate that to whatever PSI is required for whatever band that is. And that's going to just make sure through the whole shot that we have a very good constant contact and resultant UT that's happening in that area. So we can see the schematic that would be in our setup wizard. Basically, for this certain pipe diameter, we've actually taken the total number of probes, which appears to be 32, and split that for the software's purpose into two areas first. So these are all connected to one channel here on the instrument. The other half is connected on the other instrument, all going back from a single cable from these individual cables. And then we break that into what we call quadrants. So you can see there's 4 probes that are basically grouped together 8 times. So we basically group these in order to have the software be able to process them correctly and later be able to do some focusing effects later. Another schematic here just showing typically after we inflate that bladder, we want to do some level of a wiring and coupling validation. The reason for this is if we have 32 probes, we have 32 wires going into that, and then we have 2 wires coming back here. There's a lot of point sources where something could go wrong. It's not like a flaw detector where you have 1 wire. A lot of channels to check, and this has to be somewhat quickly, so we have some tools built in. We can actually see the sensitivity and the response that's happening. So if there's something wrong, we can see if a module was out, and we have subsequent ways to isolate that channel, check that channel, and make a decision whether that probe should be replaced. Maybe we didn't make good contact here, so we could go back and visually see on the bladder. Did we have the right PSI? Did we condition the pipe? We want to make sure all that is done before we take the shot, because obviously we don't want to waste time taking shots if we're not going to get good results back. So then we define the setup. So this is going back into that setup wizard idea. So basically we put in what we know about the pipe. So the pipe material, if it has a pipe size, so all the basic ANSI ASME schedules are in there, the pipe schedule along with the thickness. If it has any coating present, we can put that in for reporting purposes, for trackability purposes. And then we basically have a schematic showing us again the total number of modules, how many modules or probes are in each channel as we lay out the inspection, just so we know exactly what's going on. As a step-by-step, we'll just step through a few different screens and be able to see. At the same time, we have different indicators in the top with, telling us if we're connected to the instrument, what the status of the instrument to laptop connection is. So the first thing we're going to do is take an asymmetric scan. Again, this is our terminology for basically that full volume first shot down whatever inspected length that we want to do. And typically what we're going to do is we're going to have multiple frequencies, so it actually fire them in sequence rather rapidly. Quick to make the inspection quickly, and then when you basically get a layout. So here, if we break this down a little bit, we can see our probe collar was here at 0. We basically shot in both directions, and we can actually change that on what we display, but it's going to go as far as the ultrasound will go in each direction. We also see a large area in the beginning, about 4 foot in this case on each one, and basically this is what we call our dead zone. We'll look at that in a little more detail on the next slide, I believe, so we won't go into it here. But this is typically our output of the first shot, and then we take it from there and we'll dig deeper into the data. We'll typically try to find areas that are most sensitive to the indications we see, and then we're able to use a level of cursors to pinpoint areas and go to a raw data and do further analysis. So this is our layout here. We've taken the first shot. Again, we have the probe collar position, a small area, typically around 4 feet, 2 foot. It depends on the shot itself, but you can determine it from the data you get back. We call this a dead zone. This is basically an area that we want to be careful about examining. You can see there's a large amount of signal. This is from the actual pulsing of the system. So we have a large area where we have a lot of acoustic energy that happens. So we want to know relatively what that's going to be. It's going to tell us where to place our collar for different inspections to make sure we get as much coverage as possible. But typically we're not going to do any in-depth analysis in that area. If we saw something that was a huge concern in there, we might take another shot from a different probe position just to verify that. So we definitely do a huge amount of planning to accompany that dead zone as we decide how many shots to take, where to position the collar. So we call it an F-scan color map, which is just frequency color map. So you can see on the end here it's 15 to 85. We don't necessarily have to shoot all the frequencies. In this case, we can choose that. We usually do a 1 kilohertz step, so we're actually shooting every frequency between 15 and 85, and it lays them out in a plan or strip view. But if we don't think we need them based on the inspection, we can cut that down. We can actually change the steps, so we're not doing a step of 1 kilohertz. It's all depending, but this is a full shot. And then we have the distance. So each direction in feet, in this case, it could be in meters, is laid out, and we can adjust that. You'll also see an area that we say low power zone. It's another acoustic thing that happens at these certain frequencies in this shot. Basically, we have a certain amount of low power that exists. So if we had an indication that was overlapping that area, we know that in that area we might have a little bit less power than we would have at the other frequencies. So we'd want to keep that in mind as we do our analysis. It's a very frequency-dependent detection. That's why having 1 kilohertz steps and a full broadband range is very advantageous. So then we can go in further with these cursors that will position a distance as well as a frequency and go further into the analysis using the other tools. The way we do this is a little bit unique, but we have to have a way to manage all that data. Now, what is the scan time? It varies a little bit. Again, if you're doing all the kilohertz, how much distance you're asking it to go. But 1 to 3 minutes is typical. 3 minutes is a typical shot for a lot of inspections if we're doing a full range frequency. So it's pretty rapid considering how much it's actually performing and pulsing. So when we go to that, once we've selected a certain area that looks of interest, here we have our dead zone. We're not too concerned about that. We actually have a weld indication, flange, some things that we know exist in the scan, but these things don't correspond to anything that we know of, and they look very suspect as defects. We can actually position those cursors and start doing further analysis down on individual A scans. Typically, the first thing we're going to do is lay out what we know. So if we did that pre-scan or pre-planning, we lay out at what distance the weld, the flanges, everything exists. We can see that same dead zone that we're calling out here. And then we actually have a map of those features. So if we have bends, if we have known welds, we're going to lay all that out so that as we do the analysis, we can correlate it to the defects versus weld geometry. You can also see there's a weld here, a weld here. We actually have a system of DAC, or distance amplitude correction, that's often used to help defect quantification. So if we have welds at certain distances, we can actually predict the loss of amplitude going through a weld, and we use that to build a DAC that will help us do the defect characterization and severity later. So we can see here a few different defects and actually the ability for things that maybe don't get put into a defect category. We have C-info and other things that we can put specific notes into about them. So once we find an area that we want to look at further, we talked a little bit about active focusing. So what active focusing is actually we'll leave the bladder where it is or move it to a different location, but this is actually repulsing the instrument. But what we do is we choose. So in the back one here, we say that there's something at 10 foot we want to look at further. In order to improve the signal-to-noise ratio, get a confidence that there's something actually there, we could say pulse and focus your energy right at that 10-foot area. So we're able to do that. We actually split it up. Algorithms and the software is able to pulse in a way that focuses at a certain area on the pipe, and then we get some other tools that allow us to confidently pinpoint where that corrosion is around the pipe and the location and the severity of it. So we can see here a little bit of a module having the pipe split up into 4 main regions and pointing to a certain area. where the pipe is, and then giving us some confidence factors based on the send and received energy that we get. So again, the point there is we're able to pinpoint and reliably prove up indications, improve the signal-to-noise ratio and the confidence of detection, reduce the defect false alarm rates. This is something that has to be done actively while you're on the pipe. Synthetic's a little bit different, so this is more of a software or algorithm type thing. This can be done at any level in the inspection. It doesn't require actually pulsing the probes again. It could be done once the inspector brings it back. Maybe he didn't see something somebody else does. We can do all levels of synthetic focusing. So we can see here on the back, it's another different F-scan map or color map, if you will, where we've actually split into modular channels, and we have a layout at that frequency, 0 to, in this case, 41 feet. Probably a weld indication here, but two discrete indications here. So if we see something that we want to focus in on, we can use software to help us there. So it's basically a C-scan view of the unrolled pipe, channels versus distance at only one frequency. So we use the big map, decide which frequency to use, and then we can do these synthetic focusing at individual frequencies that see the indications the best. These are very phase velocity. They're very specific, so we actually have another wave mode that we use to do this. Without going into too much detail, it's called a flexural mode. This will help us do some of the focusing and characterization using the synthetic. So it's a post-processing tool and displays the entire inspected zone. Again, just to allude to, so then we go to that area, we go back, we do our full analysis. There's maybe 2 or 3 areas or whatever number it may be. We're going to usually go back to those areas, remove the coating, dig up that area, get some scaffolding and go up to the 20-foot mark or whatever the case may be. And if we want a quantitative value of 1,000ths or we want to inspect a whole area that we saw a lot of corrosion in, we're going to use a mapping system or a point location and get a default value. So what is the sensitivity level? We talked about it a little bit, but you know, if we take, it's very variable depending on what we're inspecting. On above ground conventional pipe, so keeping it pretty basic. If it's a pretty good condition pipe, basically we have a proven detection size. It's about 3% cross-section area. That could be better. Depending on the conditions, it might not be that as good as 3%. So it's a real variable depending on all the variables that go into an inspection. Here we just talk about some of the things that will make it vary. If the pipe is buried, if it's coated, what it's coated with, how thick. And if there's a huge amount of heavily corrosion, it's you know, completely corroded, it's going to have an effect in the total inspection area as well. So here we look at some data. So this is a 8-inch diameter pipe, schedule 40. This particular indication corresponds to about 2.8% of the cross-sectional area. So our collar was here, we shot. You'll notice here, it looks like it's very noisy, pretty typical on the lower frequencies for this to occur. Sometimes people don't use them, but we like to keep it on there. But this area here just does have some lower base level noise that occurs at low frequencies just as an ultrasonic principle. Here we have a weld probably, some other features, but we're really toned in on this one area where we see an indication at both the high and the low, and we're going to do some further analysis of it. But this particular indication is what it would look like, a 2.8% cross-sectional area compared to the baseline noise, and a very typical inspection of the view. So here's another example. So here, 8-inch diameter, schedule 40, the same example. So how we might be able to populate that. So we take cross-sectional area calculation based on the inside-outside diameter, as well as we can figure out, you know, different sizes of indications that might be able to show up around that 3% confidence factor. That is typical. So here's just another schematic of that. So this is looking at a synthetic focusing we chose to hone in on that defect. Say shoot at a certain frequency at 18 feet, and this is going to give us a more accurate and confidence of where that's at the pipe. So about 3 o'clock in this case. Won't go through the detail of this, but when we start reaching these other quadrants, there's a better chance that that's pinpointing the location circumventionally around the pipe. Very busy display just to see what an operator would typically look at. So we have the frequency color map on the top, several different features, pretty busy one. We have our probe collar position at 0 here, a dead zone that would be displayed, very close weld, different things that we've identified. Again, we'd have the schematic identifying those if we know where those welds are. Then we have several different things here because this is a pipe supported by some type of support. So we actually have pipe supports with corrosion. We have isolated corrosion, corrosion between the weld and the support. So here you can see why knowing as much information about the pipe aids the analysis and determining what things are. One other thing to see is it looks very busy because there's many different colors going on here. These can be turned on and off. These are different wave modes. We talked about the torsional, the flexural. We actually have a rebound color that shows us what direction. If it had come back from one end of the pipe and rebounded and it's going forward now, this can be turned off and turned on depending on what the operator wants to look at any point. Certain conditions and certain features also give different indicators that they learn during the analysis training to give them an idea of whether it's a geometry consideration or a corrosion or corrosion at a geometry. This is about as busy as it gets just because all those features are turned on. So here's a little bit more deeper analysis where we've laid out all those features on our pipe schematic and started to do a whole level of analysis. So we can see we have a whole bunch of defects. We also have all those supports. We've noted the end of the pipe. We've had a few areas we've identified as C-info where we wanted to put specific things specific to our application. So it looks very busy. On this particular slide, we're looking at the reverse overlay, or talking about that again. This green overlay that we can turn on and off is basically helping us identify that this particular strong signal is actually a rebound from the opposite side of the collar. So this is something that's, this energy keeps going back and forth until it completely attenuates out. So we have to have tools that can help the operator identify those features and say this isn't a feature that's actually at 23 feet. It's a rebound from 23 feet behind the collar that we're seeing going back and forth. So reporting, once we have all that, what we've done in our system anyway is it's a Word format. So everything that we've done throughout, all the active, all the synthetic, all the first asymmetric shots, anything we've done in the software can be turned on and off to show in the report. We can generate that built-in camera. We can actually take, if we saw visual corrosion or if we want to document our probe positions at each location. Really just a lot of flexibility, but it's going to basically, whatever you want to put in, a defect table, individual shots of the synthetic and active focusing that we've performed at different areas. Just very versatile, easy to configure a report. Let's go through the standards, codes, and training really quick. I won't spend a lot of time on this because there's a pretty good list. Some of the main ones, ASTM does have a standard practice for guided wave testing, focused on steel pipe work using piezoelectric, which again is what our system is. One thing we're waiting for and very eager for is ASME is publishing Article 18, which is a guided wave testing method for basic piping. Again, that's in progress. I don't have a date, but should be hopefully fairly soon. And you can see some of the other ones as we go into more international type ones. One's focused on pipeline, plant piping. Again, not published yet. GIS, NDIS, general rules. And then the BS, ES standards have some as well. Here we go a little bit further. BS, EN, these top two, so methodology and qualification certification requirements for BS and EN. CSWIP has a document. I think this details training personnel. PCN document, so general specific requirements for qualification, and also PCN certification of guided wave testing personnel, so what somebody needs to go through to qualify to PCN. And then our ASNT, ANSI, and guided wave is included now as a technology in the SNT TC1A document, giving recommended practice that can be written into guidelines for qualification of personnel, how many hours are required, etc. As far as training goes from Olympus, we really look at each situation. It depends on who the customer is. Olympus does, of course, offer training, remote and on-site technical support, as well as consultation, depending on what's needed. Basically, with the guided wave system, the need of the customer needs to be assessed first, and then you develop a training path and training plan, because a lot of operators might be familiar with other guided wave systems. They know the theory. They know the basic operation. What they need is instrument and software training only. Or it might be a customer that has no guided wave experience. So we just look at all those situations and see what the best plan, which qualification standards they need to follow, and we just come up with a training plan. So it's very varied, but those are the two basic classifications we would look at. Just to really going through, I know we're getting pretty close to our time. I'll go through a quick resume overview. So basically with a guided wave inspection, what is the key features, or how do we use it? Again, if we want to really simplify it, it's a long-range screening tool for pipe integrity assessment. To be applied and used to save removal or excavation on buried, coated, supported, insulated pipes. And then the idea is that we use guided waves to save time and money by pinpointing critical areas without unnecessary removal, scaffolding, all those other things. Before we go to questions, I just want to share my desktop really quick. I know this is a lot of information to try to shove into 1 hour. So on our website, just to point you guys to further information and ways you can get more information from us, we will be posting this post on our webinar section of the website. But you can see at our flaw detector products, we actually have a guided wave section here. An overview with a lot of basic details that we went over, details about the hardware, the software, the individual specifications or spec sheet of the system. Multimedia is quite good. There's a very good overview video that we've shot that goes through a typical guided wave inspection, much like we've talked about today. And then obviously brochures in different languages that we can get you. And also access to get more info. So if you go, you can request a quote. It'll go to the required person for this. You can contact an Olympus specialist, and you can request a demo. So if you would like somebody in your region to come out and demo the guided wave system, we can put you in contact with them. So it's a very good place to go to kind of fill in your information gaps. See if I can go back to the presentation here. We are at the end of our 1 hour. We have about 2 or 3 minutes, so I'm just going to look. If you give me a few minutes, I might go quiet here. I'm just going to see if I can take 1 or 2 questions from what you've given us. And the ones that weren't answered, we will be addressing them one way or another via email or some other way. Okay, so there's a question. I think we covered it, but to make sure everybody's clear, where is the collar placed? Is that area of pipe coating required to be removed? It depends on the inspection. Typically, yes, we would remove a small area of the coating. Again, there's a lot of variables when it comes to piping and the coatings and everything else, but typically we would remove the small area, 4 or 5 inches, that the collar needs to be placed in order to have access directly to the pipe wall. That's really what we're trying to test for the most part. See if I can find another one while we just have 1 or 2 more minutes. The question about plastic pipe. Can the pipe be polyethylene or maybe HDPE is what they're referring to? Typically, it is quite possible. Right now, we haven't done any in-depth tests within Olympus on polyethylene. Every type of pipe material, basically for the software to work, the focusing tools, distances, everything, there's a certain amount of algorithms. It's really the power of the software. We need to be able to predict and do certain things. So different materials require software development, basically. So right now we're not focusing on plastic or polyethylene pipe, but we know it's a huge part of the industry, and there's a growing number of plastic or high density, low density polyethylene pipe going into the industry. So It's definitely somewhere the technology might go on our software side, but I can't give you any more specific on that point right now. So that's really it. I do appreciate the questions. It looks like we do have some other good ones, so we will definitely try to get to those. Any more questions, again, besides where I pointed you, you can start at our website. And I just want to say thank you one more time for joining us today. And as always, it's a pleasure.
On behalf of Olympus, I'd like to thank all the attendees for joining us, and thank you, Nick, for your expertise and participation in today's event. We hope this material presented was informative and useful. This webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. Everyone who registered for this event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for attending, and we'll see you again next time.